My name is Swati. Me and my friend Sandeep Pranav Prayush are excited to present our project titled Smart Networks A and ML Approaches to Modern Networking Challenges. Together, we explored how artificial intelligence and machine learning can be introduced to improve modern computer networks. Moving to introduction slide. In this project, we focus on how AI can apply for traffic classification, animal detection, and network optimization. Our aim is to show how AI-based approaches outperform traditional natural manual methods, making networks faster, more secure, and easier to manage. Modern networks are becoming increasingly complex with diverse types of devices, applications, and real-time data traffic. Traditional networking approaches like static rule-based system and manual configurations are proving to be insignificant to handle this complexity. These methods are not only time-consuming but also prone to human errors and limited scalability. To address these limitations, AI and ML approaches offers automated intelligent solutions. AI can automate traffic classification by learning from data patterns, detect anomalies in real time before they escalate into attacks, and optimize network operations dynamically without human intervention. In this project, our approach focuses on applying AI for traffic classification, animal detection, and network optimization. We also performed a detailed evaluation comparing AI-driven methods versus traditional techniques to show measurable improvements in network efficiency and security. Moving to literature survey, recent literature highlights the significant role of AI and ML in advancing modern networking. AI-based models, particularly convolution neural networks and concurrent neural networks, have shown remarkable performance in traffic classification tasks, achieving accuracies above 98%. Traditional methods like deep packet inspection are increasingly seen as limited due to the dependency on manual rules and inability to adapt to encrypted or evolving traffic patterns. AI-driven models excel in animal detection by identifying abnormal behaviors in real time, which is critical for modern network security. Additionally, AI techniques enhances security in software-defined networks by enabling dynamic threat detection and response mechanisms. Overall, the survey determines that AI outperforms traditional networking methods by offering great accuracy, scalability, and adaptability. Moving my friends will expand.
Thank you, Swati. So, to start with, hello everyone, I'm Sandeep. I'll be presenting the system design and implementation of our project. So, modern networks are facing increasingly challenges in terms of complexity, security threats, and performance bottlenecks. To tackle this, our system is built around three core AI-driven modules. Those are classification module, anomaly detection system, and network optimization engine. To start with the first one, the traffic classification module. Here, this module extracts features from network traffic in real time, such as protocol type, timestamp, and packet size. These features are then fed into the machine learning models like decision tree and KNN, which are trying to classify traffic types. This helps the network understand and how different applications behave and react accordingly. Coming to our second one, anomaly detection. For security and our system includes a supervised learning based anomaly detection unit. It continuously monitors for the unusual traffic patterns or unauthorized accesses. This model identifies threats by learning from historical label data, enabling it to detect both known and novel attacks with high accuracy. Coming to the third one, here the optimization engine dynamically adjusts network band parameters like bandwidth, allocation, and latency threshold using insights from the traffic classification and anomaly detection module. This ensures that the network remains responsive and efficient even during heavy load. Coming to the much more important thing is SDN integration. All of these AI modules are integrated with a software-defined networking framework. The SDN allows centralized control over network behavior, making it easier to deploy our AI-driven decisions in the real time. It adds scalability and flexibility to our system. So moving to our system implementation, to bring the design into reality, we use the following tools as step. The first one is Mininet, Wireshark, Pandas for pre-processing, model training, and the algorithms decision tree KNN, and later we have done the performance evaluation. To speak with the first one, Mininet, we used Mininet to stimulate a realistic network topology. It provides a virtual environment to test how traffic flows through different nodes and switches, just like a physical network. And the next one is Wireshark. For data collection, we used Wireshark to capture live network packets. These packets were then exported and preprocessed for future extraction. The third one, pandas for preprocessing. The captured packet data was cleaned, labeled, and preprocessed using Python's pandas library. We selected important features such as protocol, port numbers, and time intervals between packets. And coming to our model training, we trained two models over here. Our first model, a decision tree classifier, which achieved 100% accuracy in the classifying network traffic. And the second one is KNN. In KNN, it has scored us 93.1% of accuracy. These models were implemented using Scikit-learn, a popular Python library for machine learning. And for performance evaluation, we tested all these models on unseen data to validate their accuracy and efficiency. We also evaluated how well the system detects anomalies and optimizes traffic. In summary, our system effectively combines AI with networking by using traffic classification, anomaly detection, SDN based optimization. Through stimulation and real world packet analysis, we demonstrate how intelligent system can make the network more secure and efficient and scalable. Thank you.
Yeah, thank you, Sandeep. So now I'll explain the code implementation. So coming to the import libraries. So we have pandas for reading and manipulating data. Then we have the OS library, which is imported for which is useful for file operations. And then we have the scikit-learn, which provides tools for model training, evaluation, and splitting data. Then we have NumPy, which helps with array and numerical operations. And then we have the matplotlib and Seaborn for data visualization. Seaborn makes like good plots. And then we come to the part two, which is loading and preparing the data. So features such as time, source, destination, and length are loaded here. Label is the output we want to predict, which is called protocol. And coming to the third part, which is getting the features. So we have the function called get_dummies, which converts categorical columns like source and destination into binary columns. This allows machine learning models to understand and process them. Then we split the data set for training purposes. So we go with the flow of splitting the data set into 80% training and 20% testing. So the random state, which is 42, ensures reproducibility. And then we have the model initialization, which can be explained as the model one, which is tagged to a decision tree, which learns the decision rules, and model two, which is a k nearest neighbors model that classifies based on similarity to training examples. And then we come to the model training. What it does is the model learns from the training data. Then we have the model prediction, where the models generate predictions using the test set. Then what we do is we convert one-hot encoded labels into class indices. So we have a function called argmax, which converts one-hot encoded vectors back to class labels, like a vector of 0, 1, 0, 1, 0, which is directed to 1. So this helps in evaluating performance using classification metrics. And then we come to the accuracy. So accuracy is the ratio of the correct predictions to total predictions. So high accuracy means better model performance, which is what people want. And then we have the confusion matrix calculation. So a confusion matrix is a matrix which shows true versus predicted classifications. Each row is an actual class, and each column is a predicted class. And then we have the confusion matrix visualization, which can be explained as two side-by-side heat maps showing confusion matrices. And this makes it easy for us to compare the two models visually. And now I come to the visual part, which is the bar plots. So a bar chart comparing the accuracy of both models is presented here which helps us to quickly identify which model performs better. So to summarize the whole code part, so we built and compared two machine learning models, a decision tree and a k-nearest neighbors classifier. We encoded categorical data, split the data set, trained both models, and evaluated them using accuracy and confusion matrices. The results were visualized using bar charts and heat maps to clearly show model performance. And that's for my part.
Now, coming to the future works, in the future, we plan to take the system to the next level by integrating deep learning techniques like CNN, which are known for their superior accuracy in complex classification tasks. We are also exploring reinforcement learning, which can help network make adaptive, real-time decision based on changing condition. This will make our system more dynamic and self-adjusting. And another important area is deeper integration with software defined networking, which is SDN. This will allow AI models to directly control network flow in real time, making traffic management more intelligent and efficient. We are also looking into the edge AI, where processing happens close to where the data is generated. This will reduce latency and improve responsiveness, especially important for time sensitive applications. Finally, federated learning is our radar. This will enable multiple networks to train model collaboratively without sharing the raw data, improving both scalability and data privacy. This enhancement will push the boundaries of how AI can transform modern networking. And going to the next slide, uh, conclusion. To conclude, our project demonstrations that AI and machine learning can significantly enhance the performance, security, and automation of modern networks. We've shown how traditional approaches often fall short when dealing with today's complex traffic and security needs, and how AI models like decision tree and KNN can deliver high accuracy in tasks like traffic classification, and anomaly detection. With the tools like Mininet, Wireshark, and Scikit-learn, we successfully implemented and tested a prototype system that outperforms conventional methods. As our network continue to grow in complexity, the roles of AI will only become more crucial. Our works lay the foundation for future innovations like intelligence, adaptive, and secure network system, especially with the rise of SDN, edge computing, and eventually 6G technologies. Thank you.